Hi everyone, Ryan Jackson here. Hope you're doing well. Today is April 30th of 2021, which means May is right around the corner and May is Electrical Safety Month. So I decided to do a series of videos covering NFPA 70E, which is the standard for electrical safety in the workplace. And I figured what better place to start than with what we call an electrically safe work condition, because that really is kind of one of the main goals of 70E is to establish and verify an electrically safe work condition. So we're going to talk about what that means and how you do it, and perhaps most importantly, why you would do it. Let's go ahead and get started. This is based on the 2021 version of 70E. And again, we're going to be talking about an electrically safe work condition. So bouncing around through a couple of different sections here in the standard, I want to start very quickly with a concept in 110.5H3, which is the hierarchy of risk controls. It says that when we're doing a risk assessment, we have to perform it in this specific order. The first thing that we want to try to do whenever possible is to eliminate the hazard. And then you'll notice the last option is personal protective equipment. There used to be kind of an ideology. Well, of course, back in the day, the ideology was just shut up and work energized and leave me alone and go do it. And then we kind of started evolving once OSHA and 70E really started to become well known. We really went 180 degrees away from that and said, okay, I still want you to work energized, but here's an astronaut-looking suit. Go work it hot and shut up. And that's better than not wearing any personal protective equipment, but that is not what we want to be doing. Personal protective equipment is the least effective way to avoid an incident. The most effective way, of course, is to eliminate the hazard. Then having an incident can't happen. And of course, OSHA and 70E both consider that the first priority. So the first thing we want to do is try to eliminate the hazard, and that's what we're going to be focusing on today. If we can't eliminate the hazard, maybe we can substitute it to a lesser hazard, work on the control circuit instead of the 480 volt circuit, perhaps. Engineering controls, awareness, administrative controls, and then again, the last option would be PPE. So examples. Eliminating the hazard means we create an electrically safe work condition. And again, that's the topic for today. We could use low voltage controls instead of line voltage. We could use arc energy reduction, signage, training, planning, and then again, the last option is PPE. So we want to focus on eliminating the hazard. Now, why is it so important to take electrical safety seriously? You know, we've all heard stories of doom and gloom, and maybe we've seen videos of some terrible events. But I'll tell you where it really hit home for me in a major way is the first time that I taught the subject, and my friend Ross was in the room at the same time. This is my friend Ross here, and as you can see, Ross looks a bit different than some of us. Ross, as you can see, is missing both of his arms, and he lost both of his arms in an arc flash incident. And what you can't see is he's also missing one leg that happened in that arc flash incident. So if you can think about Ross and think about the changes that he had to go through in his life, not just the pain and the suffering involved with the actual procedures, but how different has his life been over the last 30 years without the use of both arms and one leg. He lost the arms and leg in an arc flash event when he was 29 years old, and he spent the last 30 years of his life without the use of his arms and leg. So it is a serious issue, and it's one that I hope you'll take seriously as well. So how do we eliminate the hazard? Well, we create what's called an electrically safe work condition. So 110.3 tells us when we need to have an electrically safe work condition. And I know we haven't defined what that is yet, but please bear with me and know that we will define it very soon. So conductors or parts operating at 50 volts or more must be put into an electrically safe work condition before an employee performs work if the employee is within the limited approach boundary. Okay, so we have a couple of different boundaries in in NFPA 70E. One is an arc flash boundary, and that's how far away, from a potential arc flash source you would need to be in order to avoid a second-degree burn. We have the limited approach and we have the restricted approach. And the restricted and limited approach are both having to do with shock protection. And that's what we're talking about here. So if the employee is within the limited approach boundary, then we need to establish and verify an electrically safe work condition. So what is the limited approach? Well, the limited approach is actually pretty easy to figure out because it's just a voltage issue. For 480 volt, like what we have here in the photograph, the limited approach boundary is 3'6". So if I have the covers off, right, because with the covers on, then there's not a limited approach boundary because there's no shock hazard. Can you walk right up to a panel and turn on and off a circuit breaker in the NFPA 70E? Sure. Assuming that it's in normal operating condition, covers are closed and everything else, yeah, you can go up and you can touch the panel without putting on any PPE or without shutting anything off. What we're saying is if there's a shock hazard, such as the covers being removed, then we have a limited approach boundary, and we need to have an electrically safe work condition if you're within the limited approach boundary. Now, for 480 volts, that boundary is 3'6". And if you stop and think about it for a minute, that's a pretty reasonable requirement. If you've removed the cover off of the switchboard here and you're within 3'6", so pretty much the working space. I mean, if you're within 3'6" of the energized 480 volt equipment, you're pretty much right in there. You really need to have that thing shut off and put into an electrically safe work condition. Now, the definition of the limited approach is the approach distance from an exposed energized electrical conductor or circuit part where a shock hazard exists. Now, again, here in the photograph, the covers are closed. There is no limited approach boundary. But once I open those doors and remove any sort of dead fronts, then I have a shock hazard and I have a limited approach. So for 50 volts up to 750 volts line to line, the limited approach boundary is 3.5 feet. And if you're not familiar with 70E, this is what it actually looks like. You can go down the voltage and measure to exposed fixed surface circuit parts, such as inside of a panel board, switchboard, switchgear equipment. 50 to 750 volts is 3.5 feet. Now, to an exposed movable conductor, like a wire that's in the open air and can move around, well, then it's 10 feet. I don't think that issue comes up quite as often as a fixed circuit part, so we'll focus on the fixed circuit part for today's discussion. So it's 3.5 feet for voltages of 50 volts up to 750 volts line to line. And for most of us, that's where we spend most of our time, right? 480 volts, 122.08, 122.40. So most of us, the limited approach boundary is 3.5 feet. So I have to have an electrically safe work condition if I'm within 3.5 feet of exposed live parts, if you will. If I keep reading, I also need to have an electrically safe work condition if the employee is interacting with equipment where conductors or circuit parts are not necessarily exposed, but an increased likelihood of injury from exposure to an arc flash hazard exists. All right, so we've got this individual doing whatever it is that he is doing. It looks like we don't even have the required working space in 110.26, so there's a violation of the NEC. But whatever type of work he's doing, he's got an energized switchboard here, or switch gear perhaps, and he's doing something in the back of it. That is probably an increased risk of injury. He may not be exposed directly to the energized parts, but he's doing something that increases the likelihood of something bad happening. So this should be de-energized and put into an electrically safe work condition. Let me give you another example of an increased risk of injury or increased likelihood. What we're looking at here are some medium voltage power circuit breakers. And if you're not familiar with them, These are the contacts. You've got 3 on the line side and then 3 on the load side of these circuit breakers. And these get racked into a large piece of switchgear. Now, one of the components to these large circuit breakers is they're on kind of a dolly system, if you will. And to move them from point A to point B, you put this bar inside of there and you drag it around, kind of like the handle of a wagon, if you will. So, what we're looking at in this photograph here is an actual incident, a near miss, as it's called. This is at a place where I teach every year. They had racked out this circuit breaker, and when they pulled it out, they realized that someone, potentially years ago, had left this bar inside of the equipment. So, you talk about an increased likelihood of injury. When they were taking that circuit breaker out, if they had jostled it even slightly, you can see that this bar might have fallen line to line and we would have had a 12,470 volt arc flash happening. So that would be an increased likelihood of injury. So if I'm in the limited approach boundary, or if I'm doing something that has an increased likelihood of an injury, then I need to create and verify an electrically safe work condition before performing the task. What if you can't shut the equipment down? Is it ever allowed to work on energized equipment in 70E? Well, yes. The 70E doesn't say thou shalt shut everything down in all instances. There are times when that's not possible. So when are you allowed to work energized according to 70E? Well, that's where we get into 110.4, additional hazards or increased risk. Energized work is allowed if the employer can demonstrate that de-energizing the equipment actually introduces additional hazards or increased risks. All right, now what I'm showing here in the photograph is, of course, a hazardous location. We've got all of these containers of gasoline. You would never work energized in that building. Think about it for a minute. You've got all the gas vapors floating around in that room. Any sort of arc, spark, or bad thing would quite literally blow up the building. So you're not going to be working energized in here. So why am I showing a hazardous location? Well, because sometimes shutting off ventilation systems for a hazardous location could actually introduce additional hazards or increased risk. Now, when we say additional hazards or increased risk, well, an increased risk from what? We're increasing it. So what was the initial risk that we're increasing? Well, the initial risk of working energized is you dying. So an increased risk, a worser risk than you dying, would have to be demonstrated in order to allow you to work on energized equipment. This is something that really shouldn't happen very often. So an increased risk or actually introducing additional hazards does allow me to work energized. Another example that a lot of people choose to use is life support equipment at a hospital. I've talked to a lot of electricians that say, oh, you can't shut off anything at a hospital. And that is simply not true. I know a lot of people that work for hospitals or do electrical work strictly at hospitals, and pretty much none of them agree with that statement. The hospital doesn't want you working energized. If they have patients on life support equipment and the electrician explains to them, listen, I'm a human. I make mistakes. Whether it's my fault or nobody's fault, sometimes bad things happen. If I'm working in this panel and something goes wrong, you're not only going to lose the one circuit that you're worried about with the life support equipment, you might lose the entire panel, or you might lose the entire switchboard or switch gear. And if it's a bad enough incident, it might be permanently damaged. So forget shutting off the breaker for 10 minutes while I do this task. We might end up blowing up a switchboard, and then you're out several weeks before we can get another one ordered. So usually, if you can explain to the owner of the facility the difference between a scheduled outage and a non-scheduled outage, usually you can explain that scheduled outages are very much preferred to an unscheduled outage. So I can work energized if we can demonstrate that shutting it off introduces additional hazards or increased risk. But again, I don't think that's something that comes up too terribly often, or at least it shouldn't. Much more commonly is infeasibility. Energized work is allowed if the employer demonstrates that the task is not feasible while de-energized due to operational or design limitations. Okay, if I have to measure voltage on a piece of equipment, well, it has to be on. So there are certain tasks that have to be done energized. And when we look at the Article 100 definition of working on energized equipment, it breaks it up into two different types. It talks about repair on energized equipment, which is where I'm actually going in and physically making changes and terminations and things. That can usually be avoided. The other type of working on energized equipment is diagnostics. And unfortunately, we're not in a position where we can verify voltage without things being turned on. So I think diagnostic is something that we're going to have to come to grips with the fact that it has to be done energized. Repair work is something we can usually avoid. So if I'm measuring voltage, it has to be on. If I'm troubleshooting, maybe it has to be on so I can figure out what's going on. If I'm doing some sort of maintenance that requires it to be energized, testing, things like that, that would be infeasibility. And the standard recognizes that that's something that has to happen. So we can work energized when shutting it off would create a greater hazard, or when I have to have it on because I'm measuring voltage, testing, things of that nature. The other times that I can work energized is for equipment operating at less than 50 volts. Energized electrical conductors and circuit parts operating at less than 50 volts need not be de-energized if there's no increased exposure to electrical burns or arcs. Okay, now, when it comes to shock, that's driven by voltage. So less than 50 volts, we're good as far as the shock is concerned. But when it comes to an arc flash, that's dependent on other variables. I'm showing a class 2 transformer, a doorbell transformer. You take the black and white wire off the secondary of that, and you're not going to be able to cause an arc flash with this thing. There's just not enough power involved. Does that mean that anything less than 50 volts is safe? Well, no, not necessarily. I could have a bank of batteries, that takes up an entire room of a building. It might only be 48 volts, but it might have a ton of available fault current. So yes, I can work energized on 50 volts and less if, and that's where we need to keep reading, if there's no increased exposure to electrical burns or arcs. So it's not just a carte blanche exception, 50 volts unless you can work energized. That's really not the case. It's only if there's no increased exposure to burns or arcs. This is where people start to get really frustrated. And they say, oh my gosh, 70E, what a joke. You can't do it. You can't even turn on a light switch without wearing PPE. Well, no. That's not true. That would only be spoken by somebody who's never read 70E, because normal operation of equipment is allowed if there is a normal operating condition. So, can I walk up to this disconnect switch here and use the disconnect, turn it off and on? Sure. Yeah, of course. That's what it's for. That's fine. Normal operation of equipment is allowed as long as a normal operating condition exists. Now, what that means is that the equipment is properly installed. Looking at this equipment, it appears that it's properly installed. So can I go up there and hit the stop and start and reverse and the handoff auto and things? Sure, assuming that it's properly installed. And of course, there's an informational note that says, look, when we say properly installed, we mean the equipment's installed in accordance with industry standards, codes, manufacturer's recommendations, and instructions. I think we know what properly installed means. It also has to have proper maintenance. Can I go into this room and start flipping circuit breakers? No, there is no normal operation of this equipment because this equipment is not in a normal operating condition. If the equipment is falling apart due to corrosion, this was actually at a swimming pool equipment room, which makes this even more frightening. Can I walk in there and turn on and off the circuit breakers? Absolutely not. We don't know what the inside of that panel board is like. We have no idea what might happen when we start turning breakers on and off. There's a very real chance that we end up having an arc flash in that piece of equipment. So normal operation of equipment is okay if we have a normal operating condition, but that means properly installed, properly maintained, and of course there's a note that tells us what that means too. Properly maintained means the equipment's maintained in accordance with industry code standards, manufacturer's recommendations. The equipment has to be used in accordance with the listing and manufacturer's instructions, so we're going to make sure that the equipment is being used for what it's actually designed to do. We need to make sure that the equipment doors are closed and secured. Looking at this photograph, can I walk up to that panel board and turn on and off the circuit breakers? Sure, it appears so. It looks like that's in a normal operating condition. All equipment covers are in place and secured. All right, well, over here on the left, there's a lot of panel blanks inside of that panel board, but hey, at least they're there, So are all the equipment covers in place and secured? Yeah. So I could go ahead and I could turn on and off this circuit breaker because that appears to be in a normal operating condition. What about the panel board on the right? Well, we're missing some of the panel blanks because we had to use them on the other panel. So is there any normal operation of these circuit breakers? No, I can't walk up and start turning these breakers on and off because I have no idea what kind of dirt or flammable materials or critters, mice and insects. Well, I don't know what's inside of that panel. So there is no normal operation of that equipment because it's not in a normal operating condition. Here's another one. This is my in-laws' cabin actually up in the mountains in Utah, and they get a little bit of snow once in a while. So my father-in-law calls me up and he says he sends me this picture, and he says, "So Ryan, obviously there is an electrical problem here, and we're gonna call the utility and get them to shut it off and everything." But he says, "Just for my own peace of mind, should I go over and shut off the breakers, for safety?" What's the answer to that? Absolutely not. That would be normal operation, right? Turning on and off the breakers, but this is not a normal operating condition. So there is evidence of impending failure. That means it is not a normal operating condition. Think about the screws that held that panel to the wall. They either broke off or they withdrew, right? And you can see if you're not following what happened here, we had like a 3-foot snowstorm and it slid down the roof, knocked the mast right off and ripped the panel off the wall. Where are those screws or screw heads, best case scenario, that used to hold this thing to the wall? They're kicking around somewhere inside of that equipment. Who knows where they are? Just opening that door might move it enough to drop one of those screw heads up against the energized parts, and we could end up having an incident. So no, there is no normal operation of this equipment because that's not in a normal operating condition. There's evidence of impending failure. And of course, we have a note that tells us what that means as well. Evidence of impending failure means evidence like arcing, overheating, loose or bound equipment parts, visible damage, deterioration, things like that. Is there any normal operation of this equipment? No. The bottom of the wireway is the little brown bits on the grass here, right? It's deteriorated down to nothing. There's no normal operation of this equipment. It's not in a normal operating condition. But if your equipment is in a normal operating condition, you can perform normal operation of equipment. So you don't have to shut off everything in order to do every single thing that an electrician might have to do. Turning on and off a breaker in a normally installed piece of equipment is okay. So, when again do we have to have an electrically safe work condition? If I'm in the limited approach boundary, which is 3.5 feet for voltages up to 750, or if I'm doing something that's an increased risk of electrical injury. If I'm doing either of those two things, then I need to have it shut off, and more specifically, I need to have an electrically safe work condition. Now, what is an electrically safe work condition? We've been talking an awful lot about it, but we haven't described what that means. Well, in Article 100, an electrically safe work condition is a state in which the conductors or equipment have been disconnected from energized parts, locked or tagged in accordance with established standards, tested to verify the absence of voltage, and if necessary, temporarily grounded. All right, so that's an electrically safe work condition. Looking at this photograph, this is either in an electrically safe work condition or it's in the process of becoming in an electrically safe work condition, right? We've got the lock, we've got the tag, so we're at least halfway through the process, and perhaps we're all the way through the process. If we read the new informational note that was added in the 2021, it tells us that, look, an electrically safe work condition is not a procedure, it's a state. It's the end result of a procedure in which the conductors or equipment are de-energized for the duration of the work being performed. All right, so this thing is locked out, it's got a tag on it. This is at least halfway through the process of becoming an electrically safe work condition. So we're going to talk about how you actually create and verify the electrically safe work condition. That's kind of the emphasis of today's topic. So 120.5, creating and verifying an electrically safe work condition. Here's how you do it. The following steps must be taken in this order to establish and verify an electrically safe work condition. All right, so how do you eliminate the hazard, right? That's the name of the game. The first thing we want to do is eliminate the hazard, and that means we create and we verify the electrically safe work condition. So step number 1, determine all possible sources of power and check the appropriate drawings, diagrams, tags, and similar. Now, this may seem like a no-brainer. I mean, look, if you've got a simple commercial building, this might be a very simple process, a very simple part of the procedure. But as you get into more and more complex systems, this might be the most difficult part of the entire process, determining what you need to shut off. You might have to shut off the power circuit and the control circuit. Or if you're in a really complex installation, you might have to look at anything that could possibly energize it. The regular source, the backup source like a generator, maybe there is a UPS system. There could be a lot of different voltage sources that you need to shut off. So the first thing we need to do is we need to take a look at the one-line diagrams and any relevant information and figure out exactly what we need to shut off. And that's one of the reasons that having up-to-date drawings is so important. I know a lot of times, once the building is built, then drawings and diagrams and things tend to kind of take a back seat. And that's unfortunate because our workers need access to up-to-date drawings, diagrams, and similar. So determine all possible sources of power. This is at a facility where I teach, and shutting off everything for this equipment can be quite a task. It says, okay, breaker location for this pump is the north end, phase 1, normal power, panel A, section 2, breaker 4, and then emergency panel breaker number 2, and the emergency power main disconnect. So I love the fact that they've actually outlined exactly what needs to be de-energized in order to work on this equipment, because sometimes, again, it's not very easy. Once you've figured out everything that could possibly power up the equipment, now we can kind of start the procedure of shutting it down. So number 2, we're going to interrupt the load, then open the disconnecting means for the equipment. All right, so looking at the photograph here, could I go up to the rooftop and just shut off this disconnect while the air conditioner is running? Sure. Yeah, I could. I could definitely do that. But let me ask you a question. Which do you think is a safer way to do it? Should I just shut off the thermostat first and then get the motor to stop spinning and then go hit the disconnect? Yeah, I think so. You're a lot less likely to have something bad happen if the motor's not spinning when you shut it off on the power circuit. So if it's possible, let's interrupt the load first with like a control circuit. and then shut off the power circuit. And we're going through item 1 right now in the hierarchy, which is eliminating the hazard, but we're not finished item 1 yet. Right now, we're kind of reducing the hazard as we go, right? And that's the second list in the priorities. So we're going to work on something in the safest way possible until we get it completely de-energized and we've removed the risk. So let's start by shutting off the motor with the control circuit if possible, and then we'll go through and disconnect the load. Here's another example, cool little piece of equipment. If you're a facility, and look, I mean, it's easy for me to spend your money, don't get me wrong, but boy, I really, really like these switches here. This is one for cord and plug connected equipment. I can plug it in, and then I've got this interlock thing so I can turn it on and off like this. It's a really nice isolation device. You can shut it off and then disconnect it. So interrupt the load, hit the switch, right? And then open the disconnecting means, unplug it, whatever that might entail. Item 3, if possible, visually verify that the disconnecting means is open by viewing the blades of the switch. All right, so in this disconnect, you can see that we've got a little window here that actually allows us to look through it and verify that the blades are in the open position. Great safety feature. Now, it does say if possible. Let's not expose ourselves to unnecessary risk. If it doesn't have a viewing window or something, am I telling you to open this up and then start working this thing and exposing yourself to that risk? No. Let's not create a hazard while we're trying to eliminate the hazard. If it's possible, if it's feasible, if it's safe, let's visually verify that the disconnecting means is open by viewing the blades or withdrawing any draw-out type circuit breakers to the test or the disconnected position. So here on the circled item here, you can see that we've drawn that thing out. So once I push it in or whatever is necessary to draw the circuit breaker out, if I can visually see that it's drawn out, that just gives me an additional measure of safety. Item 4, we need to release any stored electrical energy. Now, this could apply to like an energy storage system, potentially a battery, and certainly capacitors. And in fact, capacitors is something that was newly addressed in the 2021 version of 70E. We added a new Article 360 dealing with capacitors and created a new Annex R, which is quite substantial in the back of 70E. So if you have capacitors at your facility, take the time to read Article 360 and Annex R. But when it comes to establishing and verifying an electrically safe work condition, we definitely need to release any stored electrical energy. And item 5, which was kind of clarified in the 2021 version, we need to block or relieve any stored non-electrical energy in devices to prevent energizing the conductors or equipment. Now, previous versions of this simply said to block or relieve mechanical energy. Well, mechanical energy could be a lot of different things. I mean, that could actually be like a water valve potentially, or gears that could possibly rotate. Well, those are definitely hazards, but they're not necessarily electrical hazards, and the scope of 70E is electrical hazards. So we're clarifying, let's block or relieve stored non-electrical energy in devices to prevent energizing the equipment. So the most obvious example would be the closing springs on a large circuit breaker, a power circuit breaker like this one. Do you remember in the movie Jurassic Park? There's the famous scene where Laura Dern, she's on the walkie-talkie, she's in the electrical equipment room, and she's on the radio with the owner of the park, and he's telling her the process to go through to re-energize the park, right, to turn on the electric fence and different things. And he tells her that you have to charge the circuit breaker, and she's got the lever and she's pumping it. And all of the electrical people, when they see that video, they're just like, oh yeah, first they've ever seen in a movie somebody charging the circuit breaker. Well, what is she doing when she's pumping that thing up? Well, she's putting tension on the closing springs. When we're de-energizing equipment, we need to make sure that that tension is off of the closing springs. If the springs are without tension, then they're not going to close on us. So we need to shut everything off, figure out what to shut off, interrupt the load, We need to visually verify it if we can. We've got the draw out position on here. We need to remove any stored electrical energy. And then number 5, we need to block or relieve any stored non-electrical energy that could energize the equipment. So we need to make sure that the closing springs are discharged. Item 6. Now we need to apply a lockout or a tagout device in accordance with established and documented procedures. All right, so we say the phrase lockout, tagout, and we use that term a lot of times without even fully understanding what it means. For years, I thought that lockout, tagout was the lock and the tag, and it's not. You know what a tagout is? It's pretty much like a cable tie. That's a tagout. So here in the photograph, we have a lockout and a tag. So this is not locked out and tagged out. It's got a lockout and it has a tag. So we're going to apply lockout or tag out devices in accordance with established and documented procedures. And part of the documented procedures is we're going to be using a lockout whenever possible. The only time I would use a tag out, hopefully, is when the design of the equipment wouldn't allow me to put a lock on it. Then you might have to resort to using a tag out device. So we need to have a lockout tag out program as part of our overall electrical safety program. So this is just some parts of my kit here that I have. I've got my tag out device, that's the cable tie. I've got my lockout devices, of which there are several. I've also got my tags, which have room for my name, my date, the date of expected completion, a description of the work. It also tells people how to get in touch with me if they think that they need to re-energize it. What's my phone number? So all of this stuff might be part of a person's lockout and tagout kit. If you're at a large facility, I highly recommend personalized tags like this one. I think this is an absolutely great example of a tag. So this is at a hospital that I was touring. And when I was there, they happened to have a breaker that was locked out at the time, and I was able to snap some pictures. And it says, danger, do not operate. Well, obviously, and it says, why should I not operate it? Well, because my life is on the line, and I'm a real person, and I have a real face, and my name is Mike. My department, construction electrician. Here's my number if you need to get in touch with me. Of course, this has a pager, and it's like, what year was this? Well, this is the inter-office paging system, So anyway, I'm a big believer in personalized tags like this if you're at a large facility. And you might have people that don't know everybody else because of different shifts and everything else. So one of the most important things, though, tell people how to get a hold of you. People are much less likely to remove a lock if they can actually get in touch with you and they can find out what's going on. Lockout tagout program might be simple or it might be complex. If we have multiple people that are going to be working on a piece of equipment, we might have to have something like a group lock box where we have one master lock and we drop the key inside of this box, and then everybody puts their own lock onto this, and that way I can't open the box and get the key until everybody is complete. They can be simple little devices too. This one's kind of cool. This is a lockout device for cord and plug connected equipment. You can see that you put this lock onto the attachment plug, and then the little button sticks out, the hasp, and you can put the lock on there, and you're good to go. So whatever your needs are, there's probably already a product developed that will give you the abilities to lock it out. All right. Once we have applied the lockout or the tagout device in accordance with industry standards, step 7 is we need to then verify the absence of voltage by testing the circuit or equipment for both line to line and line to neutral or ground voltage with a properly rated tester. All right, now I want to point out that at this point of the procedure, we are not yet in an electrically safe work condition. We're still creating the electrically safe work condition. So in other words, it's still on for all intents and purposes. We are performing energized work while we are creating the electrically safe work condition. Now, can I use a meter and measure voltage on a 240-volt circuit like this without personal protective equipment? Yes, for this particular voltage, you can. So here I've got my meter. I am testing it to verify the absence of voltage, and I have to do it both line to line and line to neutral. And if you think about it, that means I cannot use a non-contact tester like the one that you might carry around in your shirt pocket, because I can't measure line to line and line to neutral with a non-contact tester, at least not up to these voltages, up for 1,000 volts and less. So I need to verify the absence of voltage. We're going to test the circuit, and we need to test the test equipment. We need to test it before and after each test, and this is often called a live dead live test. We're going to take our tester, plug it into something that we know is on and working, and we're going to verify that our tester actually works. Then we're going to verify the absence of voltage on the circuit that we're working on, and then we're going to do what? We're going to check our voltage meter one more time and make sure it still works. This is a real picture. This was my meter. On the right, you can see where I have it circled. You see the little battery symbol. I didn't stage the picture. I was using my meter, and I glanced at it, and I saw that little battery indicator. And I'm going to be honest, I don't know how long that battery indicator was on. Hopefully, it had just happened. Potentially, my battery might have been ready to die for the last 6 months. I don't know. I don't know when it turned on. So strange things happen. This seems like so much work, and it's like, oh, check the tester, check the thing, then check it again. Seriously? Well, weird things happen. Could this meter have died after I checked the meter and before I checked the circuit? Sure, that battery was ready to die. It could have happened. Can you imagine? You test it, this is good, and then you test the circuit and it says it's off. Not because it's off, but because your battery died. So once we verify that there is no voltage, let's verify that your meter actually works. We're going to check that your meter works before and after you verify the absence of voltage. Look, stranger things have happened. The last thing that we have to do as part of creating and verifying the electrically safe work condition, and this doesn't come up too terribly often, is to ground the circuit conductors if needed due to the possibility of induced or stored energy. All right, so I'm working on this light switch over here on the left. Now, I've gone through all the steps. I've shut everything off. First thing I did, of course, is I verified all possible sources and interrupted the load, went through the whole thing, locked it out, verified that it's not on. But this is also a couple of feet away from a 25,000 volt transformer. Transformers work by inducing voltage. That's their whole, that's how they work. Could it possibly induce voltage on these conductors over here? Sure. Yeah, that could happen. So if that is possible, then we need to ground the circuit conductors to prevent any induced voltage from injuring us. So not something that we have to do every time. It does say if needed. And, at lower voltages, this becomes a less common occurrence, but it's definitely not something that you need to ignore. The other item is ground the circuit conductors if they could contact energized conductors or parts. If I'm working near open energized parts like this exciter for a generator, I might need to ground the circuit parts that I'm working on so that if there's accidental contact, it doesn't energize them. All right, so those are your steps for creating and verifying an electrically safe work condition. The most important thing is that you do it. We need to understand that safety is something that we all need to be involved in. At the end of the day, we all want an installation that works, but we also want to go home at the end of the day and see the ones that we love and make sure that we can do it with both arms still attached, and that we don't have an injury that can change your quality of life. So with that said, that's the end of our first video on 70E. I'll be doing a couple of more of them as we go through May and and Electrical Safety Month. So thanks everybody for joining me. Hope you enjoyed the program, and we'll see you next time. Be safe.
Be sure to like, follow, subscribe, and ring the bell.